So let's go ahead and begin with parent functions, tables, graphs, and attributes. Okay, so let's go ahead and go to our notes. And our default parent function is going to begin with this one right here. It's f of x is equal to 1 over x. Okay, so this is our default function. Let's go to Desmos real quick and see what this graph looks like. Okay, so let me go ahead and start the graphing calculator. And we're going to say 1 divided by x. That's our parent function. So this is the default parent function of what it actually looks like. Okay, so let me come over here and I'm going to show you what's happening as far as to get this graph. So let's say that we're going to input all these x values into the function right here where x belongs to see what would y equal. Okay, so this would be a negative 1/3, negative 1/2. This is just negative 1 because 1 divided by negative 1 is negative 1. And then this is 1 divided by 0, which is undefined. This is very important here to start off that we can't divide by 0. Okay? So then we have 1 divided by 1, we'll get a positive 1. 1 divided by 2 is 1/2, and then 1/3. So if I were to graph these points, well, let me do a little bit more. Let me now look at plotting these x values inside here, because by hand, this is what we need you to do. Okay, so 1 divided by a negative 1/3. Now I know this looks a little weird, but you could write it like 1 divided by a negative 1/3. And this is highly recommended because you learned in 5th grade when you're dividing fractions, you can change this to multiplication and then do the reciprocal of that fraction. So this will give you a negative 3. So by hand, that gave us a negative 3. Okay, let's try to do that again, but this time with negative 1/2. So if I have this negative 1/2 in the denominator, then that's the same as 1 divided by negative 1/2, which is the same as 1 times the reciprocal, which is going to give us a negative 2. Okay, so we have negative 3, we have negative 2, and then 1 divided by 1/2, it's going to be the same, only it's not going to be negative, so it'll give you a positive 2, and the other one would give you a positive 3. Okay, so this is the table of a rational function. So the first thing that I want to identify is this undefined piece. Okay, and it's basically saying we cannot draw a point or anything there at x is equal to 0 does not exist. So when x is equal to 0, because it doesn't exist, I'm going to go ahead and make this into something called a vertical asymptote. Okay, so right here at x is equal to 0, this is the line that the graph will approach but never hit. And you saw that verified over here that it's approaching x equals 0. Imagine that there's a vertical line here at x is equal to 0. It will approach it very, very close. Very, very close it'll approach 0 as this graph goes to infinity. And it'll approach 0 from the left as this graph goes to negative infinity. And thus, that's your vertical asymptote. Okay? All of these other points, we're going to have like negative 3, negative 1/3. Negative 2, negative 1/2, negative 2, negative 1, negative 1, negative 1. Then we have 1, 1. Then we have 2, 1/2. Then we have 3, 1/3. We also have a negative 1/3 that goes down all the way to negative 3. Negative 1/2 goes to a negative 2. And then 1/2 goes to a positive 2. And 1/3 goes to a positive 3. And thus, this is the graph that we get. Okay, so there's that first quadrant. Over here, here's the third quadrant. And the default is going to be in the first and the third quadrant, as you see here. Now, if I ask you, scan this graph to test its domain, you're going to use basically a vertical line that you're just going to scan and move from left to right. And you notice that all of these values are going to exist everywhere except for 0. So you're going to write this as negative infinity to 0, union 0 to infinity. Okay? Or you can say when x's are not, so let's say or x's are not equal to 0. So that's another way that you can say it. Now, just like we have a vertical or vertical asymptote, we also have a horizontal asymptote. So the horizontal asymptote is the line that as you go to infinity or negative infinity, this graph will approach. Okay? So as I go and I get bigger and bigger and bigger on the x as I go to the right, this graph is going to get closer and closer and closer to zero, never to touch. Over here, it'll get closer to zero, not to touch at the end. Okay? So the range is going to be everything up here going up and everything down here going down, but not at y is equal to zero. Okay? So the domain dealt with that vertical asymptote. Okay? Let's say that vertical asymptote, we'll write it in blue, at x is equal to zero. And that's why, because it's a vertical asymptote, this is why you can say where x is not equal to zero is where the graph would exist. Okay? And the range is talking about that horizontal asymptote that we just saw, where y is equal to zero. And it's going to yield the fact that, okay, so the range is all the y's that are not zero. And you could also do the same. Y's that start from way down here, going to zero, not to touch, and then to keep going to a positive infinity. And you could write that as the following. Negative infinity to zero, union 0 to infinity. It looks a lot like it had up here with the domain. Okay. So the asymptotes, we just identified those just a little bit early. No worries. We're going to look at the vertical asymptote is going to be at x is equal to 0, aka the y-axis. And then the horizontal asymptote is going to be at y is equal to 0, aka the x-axis. Notice that y equals 0 is the x-axis. They're a little bit opposite. And x is equal to 0 is the y-axis. Now, intercepts. Does this intercept the y-axis? Well, it doesn't ever. Okay, and it never intercepts the x-axis as well. So you don't have any x or y intercepts. So we're just going to put 0 or none. Okay, so the end behavior. This is very, very, very important of this unit. Okay, so the end behavior talks about as you go towards the ends, okay, end behavior is talking about as you go to infinity or negative infinity, what is the graph doing? So we'll say, what is the graph doing? Well, if I approach, and I'm going to do this with highlights so that you understand how to read this, watch. I'm going to do it like this. As x approaches positive infinity, that means as you go to the right, the graph is going to approach 0. So f of x approaches 0. Okay, let's do the other way. As I go to the left, so as x approaches negative infinity, or if I go to the left, this graph, the red graph, will also approach 0. In other words, it approaches y equals 0. Y equals 0, aka this horizontal asymptote that we had up here. Now, the only difference here is that they're just saying f of x. They're just getting a little fancy. They're just saying that the function of x is approaching 0. Okay, so let's keep going. Okay, the second part is let's look at transformations immediately. It says sketch the graphs and asymptotes of the following rational functions. The parent function 1 over x is graphed in gray. Okay, so 1 over x is your default. This is your default parent function, if you will. Default parent. And you're looking at it right there, they're already drawn for you. And we want to see, well, if this came from 1 over x, and 1 over x is here, well, then I have some extra pieces that are talking about transformations. Okay, so right off the bat, we got to look at 1 over x, because with 1 over x, just like we know we have horizontal and vertical change, this is how we can identify what's horizontal and what's vertical. So I'll give you an analogy. Remember when we did the square root of x, and we said that anything on the inside of this was considered to be horizontal change. And anything on the outside of this was considered to be vertical change, like vertical stretches, vertical compressions, vertical shifts, and all that other stuff. So I'm going to kind of coordinate this the same way, and I'm going to show you that anything with the X is going to be horizontal, and anything with the Y is going to be vertical. Okay, so notice the equation that we're going to work with is go wherever X is at, and wherever X is at, which in this case is the denominator, that entire denominator is horizontal change. Anything in front, anything on top, or anything to the right is all going to be vertical change. Okay, so that and that as well. Okay, so that's the analogy with square root functions, but now we're going to be using it for the rational functions. So let's go ahead and begin. BCAD is still the order, and if you were to look at it that way, it would look something like this. Whoops. It would be bx minus c in the denominator. BC, A would be like up front multiplying, and then plus D. This is like f of x is equal to that. So BCAD is the same order. You do the left to right horizontal piece first, and then you look at that stretch or reflection along with this shift. Okay, so that's the order. And just so you know, A times 1 over B, all this stuff could also be like A over 1, which when you multiply, they will disguise this stretch or compression as being right here sometimes. The only reason why I chose to write it with an A times 1 is because I wanted you to know that 1 is the actual default. Remember, 1 was the default that it came from. They're all 1 over x. Okay, so let's go ahead and look at these. Okay, and I'm gonna shade them as I go so that you can see the pieces that are default and the pieces that are transformations. So this is the default. This is the default. And now the transformations with order is the horizontal shift 2 to the right. And then a vertical shift 3 up. Over here, this one had a horizontal shift 1 to the left. Then it had a reflection. That's a vertical reflection because it's not downstairs, if you will, with the x. So it's a vertical reflection across the x-axis. So let me highlight that in blue. And then it will be shifted down 3 units. Okay? So I can look at transforming this and writing out the transformations, and then I can do it with points as well. However, I can whatever I want to use to be able to graph this even by hand. Okay, so we're going to say the transformations are, it was a horizontal shift 2 to the right, and the second transformation was a vertical shift 3 units up. Now, the most important thing that you want to first show of transformations, is probably the easiest approach, are identifying the horizontal and the vertical asymptotes. Okay, now we know what these look like on the original graph. They were at x is equal to 0, and they were at y is equal to 0. And what we're going to do is we're going to shift this one of these 2 to the right. Okay, so if I shift one of these 2 to the right, well, that's going to be the vertical. Okay, so this vertical one is going to shift 2 over to the right, vertical asymptote. Okay, and then you have a vertical shift 3 units up. That means this horizontal asymptote is going to shift 3 units up. So 1, 2, 3. So the center of this new graph, if you will, our transformed graph, is going to be, it looks like at 2, 3 is where the center would lie. Just like a orientation, if you will. So let's go ahead and write that out of what we actually did. Okay, the vertical asymptote dealt with the horizontal, and this was at x is equal to 2. And then the horizontal asymptote dealt with the vertical, where we shifted up by 3. And that's how we got this y is equal to 3 right here, and x is equal to 2 right here. Okay? All right, so if I want to look at x-intercepts, y-intercepts to see where this graph would go, I can plug in x is 0 to find my y-intercepts, and I can plug in y is 0 to find my x-intercepts, okay? So let me show you that with this original equation up here. Let's say that I want to look for my x-intercept. Well, x-intercepts occur when y is equal to 0, okay? So if I put 0 here, I'm going to say 0 is equal to 1 over x minus 2 plus 3. And if I just solve for x, here we go. I'm going to subtract 3 over. And then I have this piece here that I can multiply both sides by this denominator to get rid of it. So I'll multiply this by x minus 2. And when I distribute that, I get something like negative 3x plus 6 is equal to 1, because those cancel to a form of 1. And that's all I'm left with here. And now I could just finish this off by subtracting the 6 and then dividing by negative 3. So x is equal to, this is important, very important right now, x is equal to 5/3 is where my x-intercept occurred, okay? So 5/3 is like 1 2/3. So 1 2/3 is going to be about right there. That's where my new x-intercept, or where my x-intercept on this transform graph is going to occur, okay? So now let's come over here and look for my y-intercept. The y-intercept is a lot easier than all of this work, because all you're really doing is plugging in x is equal to 0 into your original equation. So if I put 0 right here, I just want to know what will it give me as an answer, okay? So I get negative 1, or 1 over negative 2, because I plugged in 0. So I get 1 over negative 2, and then we're just going to add 3, okay? And if I did this like with fractions, this is going to be the same common denominator over here. So right now it's 1. But if I multiply by a form of 1, I will get 6 over 2. Okay? So negative 1/2 is going to be added with 6 over 2, so that we can get a negative 1 plus 6 all over 2 is going to equal 5/2. Otherwise, 2.5. Okay? So x equals 5/3 was my x-intercept, and y equals 2.5. So I'll go over here to 2.5. That will be my y-intercept. Now, a couple things real quick. These are just pieces of the graph that I used so that I could see what the graph would look like. But there might come questions later of how do we write x-intercepts and y-intercepts. Just remember that the x-intercept can also be written as a point, 5/3, 0. And the y-intercept can be written as a point, 0, 2.5. Or if you wanted to put 5/2, that's perfectly fine. Okay? Just know that in this notation, when y is equal to 2.5, it's the same as if you were to put this point as 0, 5/2. And just like up here, when x is equal to 5/3, that's the same as putting it as a point of 5/3, 0. Okay? The reason why I wanted to identify the different ways that you could do that is know the context that you're doing. X is equal to 5/3 could also, if I'm looking at the context of vertical asymptotes, can be written kind of like the same. X equals something. Okay? Just like the horizontal asymptote y equals 3, looks like maybe y equals 2.5 is a horizontal asymptote. Note the context of what you're writing. Okay, so if you wrote x equals a number, it could be a vertical asymptote, or it could represent an x-intercept. Okay, so it's important for you to understand that. Okay, so if I graph these, then the new graph is going to look something like this. Okay, and then if I were to graph other pieces of this, I would see that across the way, it also has the graph that would look like this over here. Okay. Now for this next one, I'm going to do, instead of the x and y intercept, I'm going to use this next one to show you how you can use points. So this, I just did a sketch. That's all I did with this one. And I identified two key important points, the x-intercept and the y-intercept. Okay. Over here with this example, you would do the same thing to find attributes, but for the sake of time, I'm just going to show you the transformations and how you can actually plot points, okay, and key points. I'm going to show you here in just a bit. Okay, so let's go ahead and start by listing our transformations. The first one, we're going to start with the x, is a horizontal shift 1 unit to the right, or left, that is, okay, because here it is, and everything with x, or the horizontal change, is going to be the opposite. So horizontal shift 1 unit to the left, okay? So BCAD order, our next piece is this A coefficient of a -1, which is going to be a vertical reflection across the x-axis, which you could just write reflects across the x-axis. And then the third one is going to be a -3, which is a vertical shift because it's subtracting. So we just say a vertical shift 3 units down. And then we're going to go ahead and graph these and see what will this gray function, the one that's there right now, this default of 1 over x, where will it go? Okay, so here we go. Now, I'm going to look at first, this horizontal shift 1 unit to the left is telling me that I'm going to shift my vertical asymptote 1 unit to the left, because vertical, again, deals with horizontal change. Okay, so this is going to be at x is equal to, the vertical asymptote is at x is equal to -1. Okay, and then the vertical shift is going to be 3 units down. That says it's going to go with a horizontal asymptote at y is equal to a -3, okay? So a good rule of thumb is always, again, to look at these horizontal and vertical asymptotes and see where they shift, so that you can kind of orient yourself and see, where's my new center going to exist, okay? So again, we have this y equals -3 as my horizontal asymptote, and x is equal to a -1 as my vertical asymptote. Okay, so now let's look at key points on the original gray graph. Okay, so on the original graph, some key points are these right here. It's the 0, 0, where the asymptotes meet, but there's not a point actually defined. That is like a center of orientation, if you will, as far as what the graph is going to look like with the transformation. But the key points that actually do exist that I'm talking about are these two right here, at 1, 1 and -1, -1. And what I'm going to show you is how you can do transformations just with 1, 1 and -1, -1. These are my key points that I'm going to shift and whatnot. Okay, here we go. So if I looked at a horizontal shift 1 to the left, okay, let me do it this way. I'll put -1, -1 right here, and then we're going to go downward, and we're going to kind of like do the transformations and see what we'll end up getting. Okay, so the horizontal shift 1 to the left, if we did this by hand, which is definitely a goal that we want to do, is going to show that this will be 0, 1, because I subtracted 1 because it was horizontally shifted. Okay, so with it being subtracted because it was shifted to the left, I'm going to have it at 0, 1. Okay, the next thing that I'm going to do is I'm going to reflect across the x-axis. Okay, so when I reflect across the x-axis, I'm going to multiply the y value, because it's a vertical reflection, by a negative. So to be 0, -1. And then last but not least, I'm going to shift downward by 3. So when I shift downward by 3, this point is going to change. Okay, so this point is going to become 0, -4. So 0, -4. Okay, so again, let me highlight what I just did. I shifted 1 to the left, so I subtracted that. I reflected across the x-axis. That means I multiplied the y values by a negative. And then last but not least, I vertically shifted 3 units down. So that means I subtracted 3 already from this -1. Okay, so my 1, 1, which started here on my gray graph, is going to end up at 0, -4, which will be right here. Okay, now let's look at this other one, -1, -1. If I shifted it 1 to the left, I'm going to subtract, and I'm going to get -2, -1. If I reflect it across the x-axis, I'm going to multiply the y value. I'll get -1, or sorry, -2, +1. And then if I vertically shift 3 units down, I'm going to get -2, -2. Again, I shifted by subtracting 1 from the x, and then I vertically reflected by multiplying the y by a negative. And then last but not least, I vertically shifted 3 units down by subtracting 3 from that 1. So my end result are going to be these 2 points. So -2, -2, so 1, 2, 1, 2 is going to be here. And now if I did more points, I would see that this graph is going to look something like this. And notice that because of that reflection, I no longer have the first and third quadrants. This original first quadrant got vertically reflected and ended up becoming this piece down here. Okay, just like this original gray piece got vertically reflected and ended up crossing some kind of x-axis orientation and now looks like that. That's what happened by hand. So there's a lot going on with those reflections. But nonetheless, if I wanted to find the reason why I did the key points for number 2 and I did the x and y intercepts for number 1 is just to save time, but you would do both on every single equation that you would be working with.